Hello everyone and welcome. Thank you for joining this virtual presentation of our work on stacked boroughs, which I did together with Hai, Jihoon and Derek. I'm actually recording this talk in Saarbrücken, where the presentation would almost have happened, and I would have loved to welcome all of you here physically, but well, nothing we can do about that, so let's just get started. To give you some background, Rust is a fairly young programming language initiated by Mozilla and now developed by a large and international open source community with the goal of replacing C and C++ in at least some of the areas where those languages are still predominantly used. The unique selling point of Rust is that it combines low-level control, as we are used to from C or C++, with strong, high-level safety guarantees in a modern, functional-style language with industrial development and backing. And I'm actually very happy to be able to give this talk at a workshop on mainstream languages because that makes Rust officially mainstream. But the reason we're interested in Rust is less about the industrial application part and more about the fact that the mechanism through which Rust manages to achieve this unique combination of features is a type system that is unique even amongst academic languages. And the goal of this work here is to exploit the type information that this type system provides to the compiler in order to do better optimizations. So the part of the type system that's relevant here's the one-slide introduction to that. Rust enforces the key property that you cannot have mutation and aliasing at the same time. So to express that, Rust comes with two kinds of reference types. On the one hand, we have mutable references, written &muti, which allow mutation, as the name suggests, and they do not allow any aliasing to make sure that we exclude having both of them at the same time. On the other hand, we have shared references, written &t, which can indeed be shared amongst many parties, so aliasing many pointers pointing to the same thing is permitted, but none of them is allowed to mutate. In both of these cases, we have some very strong alias information. In the first case, the alias information is there are no aliases, which of course is very useful. And in the second case, the alias information is, there's still strong alias information because shared references are different from const pointers, for example, as you might know them from C or C++. A const pointer just prevents you from writing to that pointer, whereas a shared reference also guarantees to you that nobody else will be writing to the memory the pointer points to. So the alias information we have is that all the aliases are only going to be used for reads. So both of these are pieces of information that the optimizer could use to make our code go faster. Let us look at some examples of that. Here we have a test noAlias function that takes two mutable references, x and y, and then it stores 42 into the first reference, 37 into the second reference, and then reads the first reference x again and returns the value stored in there. And if this would be a C program, then there is the possibility that both x and y point to the same location in memory, and the function would actually return 37. But because x and y cannot alias, this is actually impossible in Rust, and so we know that this function has to return 42, and we would like the optimizer to just replace this by constant return 42. We can slightly generalize this example, in fact, and to this function here, where x is a mutable reference that it passed to the function, and the first thing the function does is write 42 into it, and then it calls some other function, and let us assume this other function is a function we cannot analyze. Maybe it's in a different translation unit, or for some reason we have no way to know what the function does. It could be literally anything. But even though we know nothing about the function, we still know that x is a unique pointer that cannot have any aliases that unknown function could use. So if unknown function returns, we know that x has to still store 42, and so we can still replace this return star x by a return 42 as part of the optimization process. And that's very powerful because the x here is an escaped pointer in C terms. So it's a pointer which we don't know where it came from. It was allocated by the environment, which usually means the environment can do with it whatever it wants. We cannot constrain that. But in particular when there's unknown code involved, like here. But the alias information that Rust adds on all of these mutable references is what enables us to still say something about x even though the pointer is escaped. As a similar example, we can do something with shared references, where here we have a function that takes x shared reference and y a mutable reference, and then the first thing it does is it reads x, then it writes something to y, 37, and then it reads x again. And the point is, because x points to read-only immutable data, reading it twice has to return the same value. So this function will always return true. And that is true because y, of course, cannot alias with x, because y is a mutable pointer and x points to immutable data. And again, we can generalize this to a function that takes an arbitrary shared reference x, and again, this is escaped, reads x once, and then calls some unknown function, and this time we even passing our pointer x to the unknown function. So the unknown function explicitly has access to this reference, which we couldn't have done earlier in the example with mutable references. And still, we know that an unknown function cannot write to x, because what we're passing to it is a read-only shared reference, and it cannot be mutated. So that is some great opportunity here for optimizations that go well beyond what C and C++ compilers usually do, providing the chance for Rust not just to be a safer language than C and C++, but also one that can be optimized better. There's just one problem with this grand plan, and that problem is unsafe code. So unsafe code is a feature that the Rust compiler has because the Rust developers acknowledge that sometimes programmers do things which are too smart for the compiler to understand why it is correct. So this is a sharp tool, a sharp knife that you can use, and you have to promise to the compiler that you're not using it the wrong way. That's why we have this syntactic unsafe keyword, and when you use that, like in this example function here, then you can do something very hazardous, like take the integer x, cast it to a pointer, xptr, and dereference it. And of course, all sorts of things could go hilariously wrong here, just like if you did the same thing in C. Unsafe Rust is needed, for example, to interact with, to do FFI, which means interacting with programs written in other languages. That's a very common source of unsafety in basically every safe language. And it's also used in Rust, in particular in the standard library and other low-level libraries, to get better performance. And the general idea is to avoid entirely breaking down the Rust safety story, that these APIs, these libraries, will use unsafe internally, but then they will encapsulate that behind a safe API service. So you, as the user of those libraries, don't need to worry. The promise is whatever you do with the public functions will still be safe. It's up to the implementer of the library to make sure that the unsafety stays contained inside that library. But we can also use unsafe code for some more sinister purposes, like, for example, breaking optimizations. So let us look at a way in which unsafe code provides a counterexample to the optimization that we wanted to make with test unique earlier to make it always return 42. So here we have the function again. Now we're adding a main function to call it, and so far everything is still fine. We have a local variable L, initially 13. We are calling test unique, passing it a reference that points to L, so X is a pointer to L. And well, with this program, the answer will still be 42. Everything is okay. Now we're adding a global variable, so we are seeing things get nasty. It's global mutable state. Global variable called alias. The type of alias here, starmut i32, that is called a raw pointer. Raw pointers are like the dark evil twins of references in Rust. They are not checked by the compiler. You can do almost anything with them that you want, including, for example, using a null pointer, like we did here. And to counterbalance that, actually dereferencing a raw pointer is only possible when you write unsafe, to make sure you're not accidentally using this dangerous sharp knife the wrong way. Then you are probably seeing it coming. In line 4, we are setting up this alias pointer to point to L as well. So now we are in the situation where X and alias both point to the same thing, which of course is bad because X is assumed to be a globally unique pointer, so we are seeing things going wrong here, and indeed, to not completely break the optimization, we just write this unknown function in a way that it uses the alias to put 7 into it. So if we run this program, then it doesn't print 42, it prints 7. And if we optimize it to print 42, we have changed program behavior, which of course we cannot do. That's a change in behavior, and that's very sad, because this is an optimization that we would like to do, and unsafe code says we cannot. So what options do we have here? Well, we can despair, but that's not a great option. So instead, let us find a way to say that this program here is just not an okay program to write. Programmers shouldn't do things like set up an alias to a mutable reference and then mutate it while the mutable reference is in use. So basically, you want to rule out some programs as not behaving properly. The mechanism we're going to use for that is probably well known to at least the C and C++ programmers in the audience. It's called undefined behavior. This is already present in Rust. We already have unsafe code, and you can already, with unsafe code, cause undefined behavior by, for example, dereferencing a null pointer or causing data races. So basically, when you're writing unsafe code, you're promising to the compiler that none of these things will ever happen. All of these operations come with proof obligations saying, do not cause data races, do not cause undefined behavior. The reason we call it undefined behavior is that the compiler gets to assume these proof obligations when it does its optimizations. And if you're violating the assumption that the compiler makes, then, well, we are in a magical wonderland where literally anything can happen because we are basically assuming faults. So the compiler is very happy, and it will turn your programs into a colorful version of rainbows and unicorns, which you might like or you might not, because there might not be any unicorns in your program. So the upshot is that we have assumptions associated with unsafe operations, and these assumptions are used by the compiler to justify the correctness of optimizations, and violating those assumptions is called undefined behavior. So the plan that we have for this talk here now is to explain how are we making line 9 in this program undefined behavior. We want to say that it's not okay to violate the uniqueness of mutable references here, but of course we have to say this in a way that's actually precise so that programmers know what their concrete proof obligation is. And that is where stack borrows comes in. Stack borrows is what we call an aliasing model, which means that it defines when you can use which of the pointers in your program to do which kind of accesses to which memory. You might have heard of memory models before, which are concerned with the questions when you are loading from memory, when you're reading, what are the possible values you can get. An aliasing model is entirely orthogonal to that. The aliasing model doesn't care about values, it only cares about which pointer you're using. And then if the aliasing model says the access is allowed, it basically defers to the memory model to say what actually happens in terms of the access. The goal of stack borrows as an aliasing model is to ensure that mutable references are indeed unique and shared references are immutable. Now, of course, we have a rather large design space here. We can come up with basically any kinds of rules we like. So what are reasonable bounds that we should expect our model, our stack borrows, our rules to satisfy? Well, on the one hand, the entire motivation is to get some more optimizations. So we have to ensure that stack borrows provides enough assumptions to the compiler, as in rules out enough programs to actually enable useful optimizations. And so to ensure that that's indeed the case, we have formalized stack borrows in Coq, and we've formally proven that the optimizations that I demonstrated earlier, and also some more, are indeed correct under this model. As in, any possible counterexample would actually violate the rules. On the other hand, well, this is fairly easy to achieve by just saying every program is illegal. So we have to also bound the other side of stack borrows. We have to make sure that stack borrows still allows enough actual reasonable programs to be run. And so to ensure that that's the case, we've implemented stack borrows in an instrumented version of the existing Rust interpreter Miri. And with that, we can actually now run the test suite of the Rust library and see if it contains any violations of our rules. And if it doesn't, that's a good indication that our rules still permit interesting and subtle unsafe code to be written, which of course is the point. So how does this work? Well, the key idea behind stack borrows is that Rust already contains an analysis that makes sure that as long as you're only writing safe code, mutable references are unique and shared references are mutable. This is called the borrow checker. It's part of the Rust type checker, and it ensures the you cannot have aliasing and mutation at the same time rule that I explained earlier. However, it only works as long as you're using references. Once you're using raw pointers, the borrow checker basically just gives up and leaves it up to you to make sure that you're following the rules. So stack borrows is basically taking a close look at what the borrow checker does, which the borrow checker is something static. Now the stack borrows is interpreting this as a dynamic check, and because when we're making a check dynamically, we have more information available. So now we can also extend this check in a way that it does something reasonable for unsafe code while upholding the good properties that the borrow checker ensures on safe code. So to understand how stack borrows works, we're going to start by looking at how the borrow checker works. Here's a small example of that. We have here a mutable local variable L, initially with value 13. And then in the next line of the program, we create A as a reference to L. Now in Rust, we are thinking of local variables like L as owning the memory that they are storing the value in, the 13 here. And then we are thinking of these references that are being created, like A, as temporarily borrowing that ownership. In the next line of the program, we create B by dereferencing A and then taking a reference again. So this is basically a no-op. B and A both point to L. But it's meaningful on the type system level because we're now thinking of B as temporarily borrowing from A, which, remember, again, temporarily borrowed from L. The next thing this sample program does is it stores 3 into B, which is completely fine. Then it stores 4 into A, which is also completely fine. And then it wants to store 4 into B, and the compiler says, no, you cannot do that, because the lifetime of B has ended. What does that mean? Well, As anybody who has borrowed or lent a book in real life and not gotten it back knows, when you're borrowing something, then it's a really good idea to agree upfront for how long this will last when you're getting your book back. So that's what a lifetime is about. A lifetime says how long does the borrow last. And there are two key rules that the Rust borrow checker ensures for these lifetimes. Number one, the lender, A, the one you're borrowing from, does not get used until the lifetime of the loan has expired, which only makes sense, right? If I give you a book, if I borrow you a book, I can only use the book, I cannot use the book until the loan has expired, until I get it back from you. And the other rule is that the recipient of the borrow, that's B here in this case, may only use the borrow while the lifetime lasts, which means if I borrow you a book, you may only use the book while it's borrowed to you. That also seems fairly natural, I hope. In our case, what this means is that the lifetime of B has to end before line 5, because in line 5 we're using A again. So at that point, clearly to satisfy rule 1, the lifetime has to be over, and so the lifetime is the shaded yellow area that I've indicated there. Just lines 3 and 4. But then the second rule says that in line 6, when we're using B again, the lifetime of B has to be alive, which is a contradiction to the fact that in line 5 the lifetime has to already be over, and so we have here a violation of these of this principle. We can't satisfy both of these rules at once. From this simple example, we can learn two general principles that apply to how Rust does borrow checking. Number one, borrows form this chain, right? We have L at the root as the base owner of this memory, and then we have A borrowing from L and B borrowing from A, and we could nest this arbitrarily. And secondly, the use of these elements of this chain has to be well bracketed. The pattern that got rejected here is an AB-AB pattern. And so where the second B wasn't allowed. And so basically, the goal of stack borrows is to dynamically check that you're indeed using the elements of this chain in a well-bracketed way. And it's hopefully not too surprising that to check that something is well-bracketed, we are having a stack. So we're using a stack. So that's why it's called stacked borrows. Concretely, stack borrows is an instrumented operation semantics that adds some extra state to the existing memories and values of Rust. So there's two extensions there. The first extension, the first bit of extra state that we need, is every pointer value doesn't just remember the location in memory that it points to, it also comes with a unique tag. This is needed to distinguish different pointers that point to the same thing, because as we've seen with this example, A and B both point to L. So they look exactly the same if we only care about where they point to, but using A versus using B makes a difference. We have to be able to distinguish these two pointers, and we do that by just adding a tag to them. One of them will be tagged 1, one of them will be tagged 2. Now they're not the same anymore, and we can ascribe different rules to them. And the second component is that next to for every location in memory, we don't just store the byte, like the value that is currently the current value of that location. We also store a stack, which keeps track of which pointers with which tags are allowed to currently access that location. So this example stack here indicates that at address hex 40, the pointer with the root permission, the owner, has tag 0, and it's a unique pointer. And it is, for now we will only have unique pointers. We will see how different examples of that later. And then on top of that, we have 1 in the stack, which indicates that the pointer tagged 1 was created by borrowing from the pointer tag 0. So now we have this extra state. Now we need to describe how does this extra state evolve during the execution, and what are the new proof obligations that arise that ultimately actually enable the optimizations. So let's first go to the proof obligation. The new key property that has to be upheld is that every time you use a reference or a raw pointer, that you read from memory, that you write to memory, that you're creating a borrow, the tag of that pointer has to be in the stack. If you're ever doing memory access and the tag isn't in the stack, then that's a violation of this requirement. That's undefined behavior. And the key bit about the bookkeeping is that every time we do such an access, after we found the tag in the stack, we pop away everything that's above. This reflects the idea that when you're using a pointer or reference, everything that previously got reborrowed from it has now expired. So let's look at a concrete example, at the same example as previously, in fact, for how this extra state evolves during the execution of this little program. Initially, we have just L, and while L isn't a pointer, it's a way to access this piece of memory where 13 is stored, so it also has a tag of 0. This is related to the idea of L values, if you're familiar with that terminology. If not, it doesn't matter. And then Initially, of course, the stack will also just contain that 0 at the bottom, at the root of the stack. And we always have the bottoms of the stack on the left in this presentation. Next, we are creating A as a reference to L. So we are looking for else tag 0. We find it in the stack. It's right there. And then we are creating a fresh tag 1 for A and pushing it on top of the stack. And then we do the exact same thing for B. So now we have the situation where 0 is the root owner, 1 is borrowed from 0, and 2 is borrowed from 1. Next, we're using B. So we look for B's tag, it's 2, and we find it in the stack, and it's already at the top of the stack, so we don't have to pop anything. Next, we're using A again, and this time, we are finding A in the stack, the 1 is right there, but there's something on top of it, so we are popping it away from the stack. This reflects the idea that when A gets used, B, which was borrowed from A, may not be used anymore, so we're removing it from the stack. But the very next thing we are indeed doing in this program is using B again. So we're using this tag 2 pointer, and there's no tag 2 in the stack. So we are violating the proof obligation that stack borrows requires, and therefore this is a wrong program. Of course, this program was rejected by the borrow checker, so this is not actually bad in any case. Indeed, the design goal of stack borrows is that in safe code, it's impossible to violate stack borrows because the borrow checker will make sure that you're following the rules. In some sense, we can retroactively interpret the borrow checker as being a static analysis that approximates the dynamic check that stack borrows does. So let us look at a more interesting example with some unsafe code, where the borrow checker is not able anymore to recognize that stack borrows is being violated. So this is the counterexample for the optimization that we saw before. To make this a bit easier to step over, here's the straight line version of that. It's still all the same code. We have local variable L, initially 13. Alias used to be a global variable, pointing there, and X, also pointing to L, is the argument to test unique. Then we are writing to X, and then we are writing to alias, which is the thing that was done by the unknown function. To step over this with stack borrows, again, L has tag 0, and the stack initially just has a 0 at the bottom. Then we are creating this alias, and alias is a bit different because it's not a reference, it's a raw pointer. So that has two effects. One, raw pointers, we're not tagging raw pointers. We're just treating them as untagged. We're not making any attempt to distinguish different raw pointers that point to the same memory. And the other thing is to track in the stack that this bottom permission is associated with a raw pointer and not with something else. We are marking it not as unique, but as shared read-write, because the raw pointer itself is completely okay with other accesses happening. So this reflects the fact that there is something here that is allowed to access this location, and it doesn't make any assumptions about reads or writes happening by anyone else. In the next line of the program, we're creating a reference to L. This counts as a use of L. So we are looking for L stack and the stack, 0, and we are popping away everything that's on top of it. In particular, we are popping away the bottom shared RW. And then we are generating a fresh tag 1 for X and pushing it on top. We're using X, nothing interesting happens. But now we're using alias, and alias is an untagged pointer, and there is no untagged item in that stack. So we are violating the proof obligation that whenever we're doing a memory access, the tag has to be in the stack. And that's why this program violates stack borrows. That's why this is a bad program. It's another word the program causes undefined behavior. Okay, so this should give you an idea for how stack borrows works concretely. Now let's get to the evaluation, and let's see if we're actually checking the two checkboxes that I put up here, which are kind of constraining stack borrows from the top and the bottom to make sure that it allows enough programs and not too many of them. First, let's look at let's try to convince ourselves that the optimization is actually correct, right? We have now seen that the one counterexample we had doesn't work anymore, but what is the argument that there are no counterexamples? We have a formal proof of that in Coq, and here is the proof sketch. The idea is that X will have some tag. We don't know what the tag is, but we know that after writing to X, it definitely, if we assume that this program is following the rules of stack borrows, which we may assume, being an optimization pass in the compiler, then X's tag will be in the stack, and it will also, after the write, be on top of the stack, because we popped away everything else. Then we are calling the unknown code, and we are not passing X to the unknown code. So X might have pointers that point to the same memory, like this alias pointer that we saw, but if it does, those pointers will have a different tag. And so if any of these pointers is used, that would remove X's tag from the stack, because X's tag was at the top. So if any other pointer is used, the top has to be popped off. Finally, when we read X again, we may assume that X's tag is still in the stack, because we have a program that doesn't have undefined behavior. But that means that no other pointer could have been used because, as we just discussed, using any other pointer would have removed x from the stack. And so unknown function can't access that memory, and so it still has to contain 42. There's a slight twist here that I didn't get into. For the full details of this, you can check our POPL paper. Okay, so this is the argument for why the optimization is correct in general. Now let us see about stack borrows being permissive enough to still enable useful programming. What is this interpreter that we did? Well, so Miri already existed and was already able to run some Rust code. What we did is we extended Miri with the stack and the stacks exactly the way we described in the formal and abstract just in this talk. We did this concretely by just extending the interpreter state. And what that lets us do is we can take a program, a Rust program like this one, and just run it in the interpreter, and it will crunch through it and check the stack borrows conditions and do the bookkeeping as the program runs. And if we do it with this concrete program, we will get an error. Because in line 9, Miri will notice, well, you're using this alias pointer and it's untagged, and there's no untagged in the borrow stack. So this program is not following the rules. And as such, it has undefined behavior. So this provides a way to take some Rust code and see if it's following the rules. And we did that with the test suite of the Rust library. And since then, an increasing number of crate authors actually also started using Miri as part of their own continuous integration to ensure that their unsafe code doesn't have bugs. Because Miri doesn't just check stack borrows, it also checks all sorts of other unsafe code proof obligation violations, such as dereferencing null pointers or violating data structure invariants. As part of this, so far 11 cases have been uncovered of programs that violate stack borrows. 7 of those were in the standard library. They were all accepted as bugs and fixed by the developers, by the Rust developers, and the other 4 were in external libraries and have also been fixed there. Okay, so this is all that I have to share today. There are, of course, many more things that I couldn't get to in this half-an-hour talk. First of all, I didn't speak about how stack borrows ensures that shared references are read-only. This is all, you can find all of that in our POPL 2020 paper. And in particular, we explain there how we handle interior mutability, which is an interesting twist in the Rust type system, where sometimes you actually are allowed to mutate shared references. Another feature that is explained in the paper is protectors, which doesn't just enable reads to be moved across unknown code, like in the example that we saw in this talk, but even enables writes to be moved across unknown code, which is an even more powerful optimization. In future work, we would like to explore how stack borrows interact with concurrency. We think there will not be any major issues there, because stack borrows basically doesn't, if you have a data race-free program, then the only interactions that you could have are on what is called this interior mutability that I mentioned, where stack borrows already doesn't put up any extra constraints. Stack borrows already says, well, you have any number of pointers that can be used for any number of accesses. So we think concurrency won't be a problem. However, Miri only very recently gained support for concurrency. So only now can we even start testing whether stack borrows works reasonably in such programs. Another piece of future work that we would like to tackle at some point is we have this research project Rustbelt, which we described in our POPL 2018 paper, which is all about formally proving that unsafe code indeed satisfies all of these proof obligations that Rust puts up. And now with stack borrows, we are adding a new proof obligation. And so as such, we would also like to prove that the new proof obligation is met by all of the code that we verified and just extend this framework and this infrastructure to be able to handle this new proof obligation. So that's all I got. I presented stack borrows, which is a dynamic model of the existing Rust borrow checker that ensures soundness of some intra-procedural type-based optimizations that works even in the presence of unsafe code. If you want to play around with this a bit more, Miri is integrated into the Rust playground, so you can just go to that website, type some Rust code, and in the tools menu you can execute it in Miri. Miri is also part of the official Rust nightly distribution. You can just install it with this command and run it on your test suite. And you can find more information on the Miri website, of course. And if you're interested in the other kind of Rust research that we've done, please go to the Rustbelt research on our MPI service. Thank you very much.